In the previous module, it was seen that if two individuals were to pool the risk prospects and then share the proceeds, the risk to each would go down so long as each of the outcomes of the pooled risky prospects were not perfectly positively correlated. An analogy could be given. By way of analogy, what we can see is that a wealth holder can reduce the risk by diversifying the portfolio over risky assets. The returns from which the return from the portfolio from which the return is not perfectly positively correlated. Diversification takes the form of forming an alternative portfolio with risky assets combined in various combinations. Each of these portfolios would ordinarily have different expected returns and different degrees of risk. Hence, here risk is a measure of the variation of the actual yield from the expected return. The object of diversification is to maximize the expected returns from various levels of risk corresponding to the alternative combinations of risky assets, or the alternatively to reduce the risk for various rates of expected return corresponding to the alternative portfolios. This module draws upon the previous module, and it is as per the pattern of the succeeding modules progressively slightly more rigorous in its analysis. It also draws on the statistics module some basic statistical knowledge which is necessary for it. In what follows, the risky prospects are described by outcomes in the form of return on assets, whose probability density functions are described by the expected value of returns and the variance of those returns about the expected value. In what follows, the risky prospects are described by the outcomes in the form of return on assets. The probability density functions are described by the expected values of the return and the variance of those returns about the expected value. The variance of the outcomes, that is the returns, about the expected value of the returns are a measure of the risk. Harry Markowitz, who analyzed the portfolio choice taking into account not only the return but the degree of risk as well, pioneered in this area of portfolio choice.
After studying this module, you shall be able to learn about the efficient portfolio and the efficient frontier of portfolios, identify the efficient frontier in two alternative cases. You shall be able to analyze the shape of the indifference curves of a risk-averse diversifier and the reasons for their having that shape, map the scale of preferences of a risk-averse diversifier, and understand which portfolio will be chosen by such a risk-averse wealth holder from among all the efficient portfolios. Now we will study the efficient portfolio frontier. To simplify the analysis, it will be assumed that there are only two assets. These assets are assumed to be zero coupon assets whose return is equal to V1 minus V0 upon V0, where V0 and V1 are the values of the asset at the beginning and at the end of the period. Two alternative types of assets can be thought of. One of these is a risky asset whose value at the end of the period, that is V1, is not fixed, but can take alternative values with a probability attached to each of the alternative values. This implies that R can take alternative values Ri with probabilities Pi attached to each of these values. The expected rate of return from the risky asset will be given by ER and the variance about the expected value as ERI minus ER whole square. The other type of asset is a risk-free asset whose value at the end of the period is fixed with certainty. Its rate of return is return is equal to V1 minus V0 upon V0 is then given and its variance is then 0. Two alternative cases of diversified portfolios can be considered. One is a diversified portfolio containing two alternative risky assets, and the other is a portfolio containing a risk-free asset and a risky asset. First, consider a portfolio of two alternative risky assets. Let these assets be asset A and B with respective expected returns of RA and RB and the respective variances of sigma square A and sigma square B. Let it be assumed that RB is greater than equal to RA and that variance of B is greater than equal to variance of A. A portfolio consisting of asset A and B will carry a return RP, which will be given by Rp is equal to WA-RA plus WB-RB and a variance sigma square P, which will be given by variance of P is equal to square of WA into sigma A plus square of WB into sigma B plus 2 into WA, WB, sigma A, sigma B, rho AB, where rho AB is the correlation between the returns from assets A and B respectively, and WA and WB are the weights or the proportion of the portfolio comprising of assets A and B respectively. This implies that WA plus WB is equal to 1 and that 0 less than or equal to WA, WB is less than or equal to 1. In this analysis, negative quantities of any asset or short sales are ruled out. This simplifies the analysis. Now consider an extreme case where rho AB is equal to 1 and variance of B is equal to variance of A. In such a case, diversification will not reduce the risk because diversification will lead to a variance sigma square P such that sigma square P is equal to sigma square B is equal to sigma square A, which implies that sigma P is equal to sigma B is equal to sigma A. If RB is greater than RA, then asset B would dominate asset A, and the portfolio will contain only asset B. This is because asset B has a higher expected return as compared to asset A, but with the same degree of risk. If, on the other hand, variance of B is greater than variance of A and rho AB is equal to 1, diversification would result in a portfolio with a variance of P such that variance of B greater than variance of P greater than variance of A, provided that the weights of assets A and B are positive. This implies that the diversified portfolio has a standard deviation sigma P such that sigma B is greater than sigma P is greater than sigma A. If in addition RB is equal to RA, then asset A would dominate asset B and the portfolio would consist only of asset A. This is because although both the assets have the same expected return, asset A is less risky. Hence, diversification will not be useful and the portfolio will consist only of asset A. Now consider the case where it is assumed that RB is greater than RA and sigma square B is greater than sigma square A. Then the variance of P would be given by sigma square P is equal to square of WA into sigma A plus square of WB into sigma B plus 2 into WA WB sigma A sigma B, and the standard deviation sigma P would be given by sigma P is equal to WA into sigma A plus WB into sigma B. These portfolios are on a line joining A and B, representing portfolios A and B in figure 1. For different values of WA and therefore of WB, there are alternative portfolios, each of which is a point on this line. Now consider a case where rho AB is equal to -1. In this case, the portfolio has a variance of P. Sigma square P is equal to square of WA into sigma A plus square of WB into sigma B minus 2 into WA WB sigma A sigma B, and a standard deviation sigma P of sigma P is equal to absolute of WB into sigma B minus WA into sigma A. This implies that there is a value of WA that would make the standard deviation of the portfolio equal to 0 or make the portfolio risk-free. To get this, we can rewrite WB as 1 minus WA and put sigma P is equal to 0 in the equation sigma P is equal to WB sigma B minus WA sigma A. This yields the equation as 1 minus WA into sigma B minus WA into sigma A is equal to 0. From this equation, the value of WA is obtained as WA is equal to sigma B divided by sigma A plus sigma B, and consequently WB is obtained as WB is equal to sigma A divided by sigma A plus sigma B. With these weights, the return from this portfolio is given by sigma B divided by sigma A plus sigma B into RA plus sigma A divided by sigma A plus sigma B RB. This return will be expected with certainty. This rate of return will be less than RB but greater than RA, or that RB is greater than sigma A divided by sigma A plus sigma B, RA plus sigma A divided by sigma A plus sigma B, RB, is greater than RA. This has been shown in figure 1. In this figure, there are 3 points, namely A, B, and C. Point A represents a portfolio consisting only of asset A. The line AC consists of a continuum of alternative portfolios containing amounts of asset B, which increase from a proportion equal to 0 at point A to a proportion that is equal to sigma A divided by sigma A plus sigma B at point C, and amounts of asset A which decrease from 100% to a proportion that at point C is equal to sigma B divided by sigma A plus sigma B. Similarly, line CB represents a continuum of alternative portfolios which contain proportions of asset A equal to sigma B divided by sigma A plus sigma B, and asset B equal to sigma A divided by sigma A plus sigma B at point C, to ever lessening proportions of asset A and ever increasing proportions of asset B, till at point B the amount of asset A is 0 and the portfolio consists only of asset B. On comparing lines AC and CB, it is evident that portfolios represented by the points over the half-open interval CD on line CB dominate the portfolios represented by the points over the half-open interval CA on line AC, in the sense that for the same amount of risk measured by the standard deviation of the returns about the expected return, the portfolios on CB yield a higher expected return. On line segment CB over the half-open interval DB, the portfolios yield still higher returns but at higher levels of risk. Hence, the economic agent will choose a portfolio among those that are represented by the points on CB. This then represents the efficient frontier of portfolios. On the efficient frontier, a portfolio carrying a higher risk will necessarily carry a higher rate of expected return. This can be seen to be the case of a movement along the frontier from the left to the right. The increase in the expected rate of return is the compensation that is offered for the increased risk. The slope of the efficient frontier, given by the ratio of the increase in the expected return to the increase in the degree of risk, measures the rate at which the wealth holder is compensated for taking a marginally higher degree of risk. The choice among the portfolios on the efficient frontier would depend upon the economic agent's preferences over risk and return. The cases discussed so far were extreme cases. A more probable value of ρ would be between the extreme values of -1 and 1. That is, -1 is less than ρ is less than 1. Under these circumstances, it is possible to find a set of portfolios that minimize the risk. The portfolio risk is given by sigma square p is equal to square of WA into sigma A plus square of WB into sigma B plus 2 into WA, WB, sigma A, sigma B, row AB. This can be written as sigma square P is equal to square of WA into sigma A plus square of 1 minus WA sigma B plus 2 into WA 1 minus WA into sigma A sigma B rho AB, where WB is equal to 1 minus WA. To find the value of WA, which will minimize sigma square P, the derivative of the above expression with respect to WA will have to be set to 0. That is, del sigma square P divided by del WA is equal to 2 into WA sigma square A minus 2 into 1 minus WA sigma square B plus 2 into sigma A sigma B rho AB 1 minus 2WA is equal to 0. This yields the equation WA is equal to sigma square B minus sigma A sigma B rho AB divided by sigma square A plus sigma square B minus 2 into sigma A sigma B rho AB, and WB is equal to sigma square A minus sigma A sigma B rho AB divided by sigma square A plus sigma square B minus 2 into sigma A sigma B rho AB. This is positive by the assumptions made. This portfolio is shown in figure 2. From this figure, it can be seen that the portfolios on the arc given by the open interval CB dominate those on the arc given by the open interval CA. These will be the efficient frontier of portfolios from which the wealth holder will make a choice. The choice to be made out of those will depend upon the utility function of the wealth holder. Now consider a portfolio between a risk-free asset and a risky asset called asset A, where the expected return from the risky asset RA is greater than the certain return from the risk-free asset, which is taken to be RF. The variance of the return from the risky asset about its expected return is taken to be sigma square A. However, inasmuch as there is a given return from the risk-free asset, which is certain and not stochastic in nature, the returns from the risky asset are uncorrelated with the return from the risk-free asset, or in other words, rho AF is equal to 0. Then the variance of the portfolio will be sigma square P is equal to square of WA into sigma A, and the standard deviation will be sigma P is equal to WA into sigma A. The return of the portfolio will be given by RP is equal to RF plus WA sigma A RA minus RF divided by sigma A, where the weight WA varies between 0 and 1, or that 1 is less than equal to WA is less than equal to 1. All the portfolios will lie on the line CA shown in the figure 3, which constitutes the efficient frontier of portfolios. We will now study the next topic, which is preference, indifference over risk and return. Return is desirable, and the wealth holder prefers a higher return to a lower return. Risk, on the other hand, is undesirable, and a lower degree of risk will be preferred to a higher degree of risk. A wealth holder will therefore require compensation for taking additional risk. A wealth holder's preference over risk and return can be represented by map of indifference curves. In figure 4, three indifference curves are shown. At the points A, B, and C, these indifference curves show a situation of no risk. In the absence of risk, indifference curve I3 shows a greater return than indifference curve I2, which shows a greater return than indifference curve I1. Hence, I3 is preferred to I2 and I2 is preferred to I1. Now consider indifference curve I1. A progressive movement along it to the right implies that the wealth holder is taking increasing risk. This should imply that he is moving to a progressively less preferred situation. However, the wealth holder is simultaneously being given a progressively higher rate of return, which taken by itself would imply that he is moving to a more preferred position. Along an indifference curve, a movement to the right is accompanied by a simultaneous movement upwards, so that a movement to a more preferred position on account of a higher return simultaneously counterbalances the movement to a less preferred situation on account of increased risk. On any indifference curve, the increased risk is exactly compensated by a higher return. The upward slope of the indifference curve upwards indicates the marginal rate at which the return must increase to compensate for the increased risk. As more risk is progressively taken, the marginal rate of required compensation in terms of returns increases. Indifference curves are therefore not only upward sloping, indicating that higher return is required to compensate for additional risk, but that this slope continually increases as additional risk is taken, indicating that the marginal rate of compensation required by the wealth holder also continually increases as he takes progressively more risk. This makes the indifference curves convex to the risk axis. A higher indifference curve indicates a preferred position to a lower indifference curve because for any given degree of risk, the return is greater. These indifference curves show the scale of preferences of a risk-averse diversifier. Let us now study the choice of portfolio. A rational wealth holder will attempt to get on to the highest indifference curve possible. This will be the indifference curve, which is tangential to the efficient frontier. At the point of tangency, the slopes of the efficient frontier and the indifference curve are equal. This has been illustrated in Figure 5 and Figure 6, which are applicable to the cases of portfolios with two risky assets in the first case and one risk-free asset and one risky asset in the second case, respectively. The equality of the slopes of the efficiency frontier and the indifference curve implies that the rate at which the chosen portfolio compensates the wealth holder for taking risk at the margin exactly equals the marginal rate of compensation required by the wealth holder. There is only one portfolio that satisfies this condition. Any portfolio to the right of the tangency point implies a greater degree of risk. At this greater degree of risk, portfolios which offer a marginal rate of compensation which is less than the marginal rate of compensation required by the wealth holder. Consequently, the wealth holder will reduce his exposure to the higher risk carrying asset B, even though it carries a higher return. To the left of the point of tangency, the portfolio carries a lesser risk and offers a higher marginal rate of compensation than what the wealth holder requires. This induces the risk holder to take more risk and a higher exposure to the more risky asset.
Let us now summarize whatever we have studied in this module. Diversifying portfolios by including in them assets which are not perfectly correlated reduces the risk in the sense that reduces the variation of the returns about the expected return. As we know, we have defined the risk as the difference between the expected return and the actual return. Different alternative combinations or proportions of the risky assets combined together to form an alternative portfolio, and hence different portfolios are created in this manner. Ordinarily, each of these portfolios would have a different expected yield or a return and a different degree of risk. Therefore, there is some inherent relationship between risk and return, and this is what helps in an investor to decide about the holding or the portfolio of investment. The objective of diversification is to minimize the degree of risk for a given level of expected return, or alternatively to maximize the expected return for a given degree of risk. An exercise to identify such portfolios can be carried out by the investor. This exercise will be a result in a set of portfolios which amongst them there would be one efficient portfolio, in the sense that it would yield the highest expected return for a given level of risk. Furthermore, portfolios carrying higher risks alongside the efficiency frontier would also carry a higher expected rate of return. The slope of the efficiency frontier measures the rate at which the portfolio compensates the wealth holder for undertaking higher degree of risk with a higher rate of expected return. The scale of preferences of a risk-averse diversifying wealth holder over risk and return can be represented by a set of indifference curves drawn with risk and expected returns measured on the horizontal and the vertical axis respectively. The slope of these indifference curves measure the marginal required rate of compensation in terms of higher expected return for additional risk. The slope of the indifference curves continually increase, indicating that the risk taken increases. As the risk taken increases, the marginal rate required of the required return also proportionately increases. This makes the indifference curve convex to the risk axis, which is the horizontal axis. Now, the risk averse investor, who is the diversifier, diversifies the wealth in such a manner so that he could maximize his satisfaction by choosing a portfolio indicated by the tangency of the efficient portfolio frontier to an indifference map or to a particular indifference curve within the indifference map. At the point of tangent C, the marginal rate of required compensation for increased risk in terms of increased expected return is exactly equal to the rate at which the portfolio amongst different portfolios is able to compensate the wealth holder for the marginally incremental risk.